In this lesson, we will be discussing solid geometry, which lies within the spatial reasoning unit. A couple questions we will be addressing, or our essential questions, is how do you identify cross-sections of three-dimensional figures, and how do you use rotations to generate three-dimensional figures? Before we begin addressing the essential questions, we need to first have a few vocabulary words under our belt. First, we'll start with vertex, or a plural form of that word is vertices. So these here will be considered vertices. This point here where these two edges meet, this would be called a vertex. Where these two edges meet, that's another vertex. Okay. Where these two edges meet, this would also right here be considered a vertex. For the cone, if you look right here, this would be called a vertex. And notice over here for the cylinder, there's no point you would really consider the vertex, where two edges would meet in the same way as they meet here and here. The next term is a term face, which kind of suggests exactly what it is. Notice that this right here would be considered a face. This square of this cube would be considered a face. So altogether, you would think that this prism here would have, or cube rather, would have 6 faces total. 1, 2, 3, 4, 5, and 6. Okay. The term edge, right? This would be considered an edge here. This is an edge. This dotted line here represents that it's an edge that's not visible. Same thing with this is a non-visible edge here. Here's a visible edge. All of these are considered edges. Now on to the term base. Base is essentially, you could think of as the part or the part that the solid rests on. So this would be considered a base here. You could rest on this. This would be considered a base here, and this would be considered a base in the cone. Alright, so if you recall, in two-dimensional geometry, an intersection is a set of all points that two or more figures have in common. So if you look at these two circles here, okay, this red one here and this green one here, notice that they intersect in the middle here. Okay, so this would be called the intersection of these two circles in 2 dimensions. Okay. The new term that we're going to discuss is called a cross-section. A cross-section is the intersection of a 3-dimensional figure and a plane. So here's our 3-dimensional figure, this prism here, this rectangular prism. Okay, and imagine like a plane cutting through this prism, kind of like a knife. Alright, so you can see that the shape that this would make here. Okay, if the bases of this prism are indeed squares, then this cross-section would be a square itself, as shown here. Alright, in this example, we'll try to determine what the cross-section of the cylinder is as far as its shape. Well, notice first that each base, here's a base, here's a base. Notice that each base of this cylinder is a circle. So, the cross-section that's formed by a plane that is parallel or does not intersect the bases of the cylinder, any cross-section of a cylinder made by a plane that's parallel to the bases will have the same shape as the bases itself. Alright, so since the bases form circles, this cross-section will also be a circle. Okay, but that fact relies on this plane being parallel to the individual bases here. You can imagine if we were to make this plane so that if it weren't parallel to the bases of this cylinder, okay, then it would definitely change the shape of this cross-section. Alright, so in example 1b, we're going to describe the cross-section of this cylinder here with our plane oriented differently than from example 1a. So it's going to be oriented sort of vertically like this. Since the bases of this cylinder are parallel, okay, notice how the plane cuts this cylinder. Right? If these two bases are parallel to each other, that means that this line segment formed here, since it's on the base, must be parallel to this line segment formed here on the other base. Okay. Also notice that the bases of the cylinder meet the lateral edges, or the sort of the side of our cylinder. If you think of it as a can, it would be the side of the can. the top and bottom of this can meet the sides of the can at right angles. So what we're saying here is that this angle formed between the side of the can and the top of the can is a right angle, right? So that means that this angle here should be a right angle, this angle here should be a right angle, this angle here should be a right angle, and this angle here should be a right angle. But if I have a quadrilateral with 4 right angles, what do I have? A rectangle. So the cross section is a rectangle in this case. Now for this question here, reflect on it for a while, write your answer in the notebook, and that's going to go for all reflection questions from now on. Write this question down, come up with an answer, and we'll discuss it in class. The same thing with this question here. And feel free to pause me at any time so that you can go back and forth and write these reflection questions down and think about them, but come prepared to class with an answer to these questions. Alright, so on to three-dimensional transformations. You've learned how to perform transformations in a plane, like rotations, glide reflections, translations, and other reflections of that sort. But up to this point, we've only talked about transformations in a plane or on a coordinate axis. But transformations can also be carried out in three-dimensional space. There's no reason why. For example, let's say you had a can. You could easily take that can, rotate it 90 degrees in some way, and you've basically essentially just formed a transformation of that three-dimensional figure. What we're going to investigate now is how we can actually rotate a two-dimensional figure around a line so that we can generate a three-dimensional figure. Our goal for this example, example 2a, will be to generate a three-dimensional figure using a two-dimensional figure. In particular, in this example, we're going to be using a triangle, okay? And we're going to be rotating this triangle around the axis or a line that goes right through one of the legs of the triangle, okay? In order to model this rotation, what you might do is you can trace and cut out a triangle, and then tape the triangle to a piece of string so that one leg of the triangle is attached to the string, and then hold both ends of the string and twirl it between your fingers so that you can see the three-dimensional figure generated by the rotation. Okay, once you've done that, you're going to sketch the figure that you obtained, the three-dimensional figure. You're going to sketch the three-dimensional figure that you obtained by the rotation in this box here. You'll notice if you complete the experiment from the previous slide that you'll actually obtain a three-dimensional cone from the rotation of this two-dimensional right triangle along an axis that goes through one of the legs of the triangle. So this would be essentially your string. Okay, this would be the triangle that you cut out on your paper. And once this thing starts twirling, you'll see that in 3 dimensions you'll end up getting a cone. So the figure that's generated by the rotation is a cone. Now we're going to look at rotating a different figure, in particular a rectangle, around a line that goes through the height of the rectangle. Okay, so you're going to do the exact same thing. You're going to cut this rectangle out, take a piece of string and tape it to one of the edges of your rectangle and twirl it as you did before, and you're going to sketch your resulting three-dimensional figure here. Right? You're going to sketch your resulting three-dimensional figure here in this space. Once you've done that, you'll notice that the figure that is generated by the rotation is a cylinder. Here's the original rectangle that we started with here. Okay, and if it rotates in this direction here, along this axis, here's the axis of rotation, it'll end up sort of sweeping out a three-dimensional cylinder. Alright, so now we have answers to our essential questions that we started out with trying to address. Just to remind you, those questions were: how do we identify cross-sections of three-dimensional figures, and how do we use rotations to generate three-dimensional figures? Well, use visualization and properties of three-dimensional figures to identify cross-sections of three-dimensional figures. So what that means is, if you imagine your plane cutting through your three-dimensional figure and visualizing what the cross-section will actually look like. Also, to address the second part of our essential question, you use rotations to generate three-dimensional figures by rotating a two-dimensional figure around some line. Alright, and to summarize this lesson, write a journal entry in your notebook in which you illustrate and describe two different ways to use a rotation to generate a cylinder. Then, illustrate and describe two different cross-sections of a cylinder.